So,
I was using this.
okay. And basically the idea that we store again some history. So we store iterates at the previous steps. But what we store, we do not store the iterates, but we store the errors. So in the linear case, we will call it residual. The residual is just the difference between the left side of the equation and the right side of the equation, evaluated at the same point. Right? So if x would be the solution, the residual is 0. So we do not even in fact require that the original iteration converges. We only need to be sure that there is a fixed point. Of course, but the typical situation it converges but slowly. So we use this history of the updates and we compute the next iterate as the fixed point plus the correction of the previous residual, where alpha, there are parameters that we will need to determine. But independent of which parameters we take, if we fix m, then x equal to x star is again the fixed point of this equation. That's obvious. So if x star equals f of x star, then it satisfies also this equation with the same alpha. So what we do, we put a constraint on alpha that all alpha sum up to 1. And we do formally not a very correct thing, but still, we want to minimize the error. Want to minimize the error. So it's motivated by the linear case, but we just formally generalize it to a non-linear case. And what we have now here, we just have a linear least squares problem. So this is a least square objective that alpha times the known vector is the norm of this guy is minimal, and there is a linear constraint. So there is very easy to come up with a formula for solving this, and it's very cheap. And of course, this can be pre-computed. So you do not need at each iteration to compute the mapping phi, which may be time-consuming. The mapping may be time-consuming, but you pre-compute. So the complexity of this iteration is the same as the complexity of this iteration, but the convergence is typically much faster. So if you have a first-order method, which means has a geometric convergence, sometimes this method, the Anderson acceleration, gives the super linear convergence, even quadratic. So you can show that there are final results. You can show that this is so-called quasi-Newton method. So in the linear case, this is equivalent to GMS. That's a funny observation. If you do this, and this is a linear mapping, this is exactly equal to the GMS applied to the matrix identity minus phi. So this can be called a nonlinear GMS. It was also called direct inversion in iterated subspaces. That's nice looking. The acronym is nicer, DIIS. Used for many years in chemistry, and also it's useful when you have oscillatory convergence, when you have convergence like this. And that's very typical in many fixed points. So you do flip, it's so-called flip-flop convergence. Plus and minus, plus and minus. Using such kind of things, the convergence. So yeah, so we have written several papers using this. This idea is really very cheap. You have a slowly convergent method, you have a subroutine that computes the right-hand side. Just put on top Anderson acceleration production. So, yeah. If you have a second order method, this doesn't help. There is a recent paper, really recent, that shows that for quadratic conversions, it doesn't help. There also a relatively recent paper, one of the authors is Voigt, well-known guy from optimization, which gives the sort of global convergence proof for Anderson acceleration. So people still researching this kind of things, which is nice. So that is all for iterative some that we didn't mention. There is so-called quasi-minimal residual, QMR, and probably that's all. That's all that is implemented in SkyPy, Linux, SPSolve or something like that. So it's CG, ICG, ICG stub, GMRES, MinRes, and QMR. I think that's all. So the GMRES is the one that doesn't have the short-term recurrence relations. And you'd have to do restarts. CG is the best for symmetric positive definite. BCG stub is probably the method of choice for non-symmetric if you have the access to matrix directed product. Still, if the condition is large, there is a problem. So we need to have a certain preconditioners, and preconditioning linear systems is sort of an art. Constructing a preconditioner for a given linear system. So there is no universal recipe that provides the best preconditioner. But again, there are classes out of which you can select and try different ones. And then many of them have hyperparameters which you tune as usual, and so on. The definition that I already showed you in the last lecture, that's a repetition. So you have a linear system. You can do either so-called right preconditioning or left preconditioning. So typically it's written in terms of multiplying by the inverse. So we solve a linear system with a matrix A times PR minus 1, or the linear system with a matrix PA minus 1A. Or we can even multiply from both sides. Probably it happens rarely, but sometimes it's needed. So what we need, and then we need two things. First thing is that the condition number of the product of this matrix A times PR minus 1 is better than the condition of A. So in principle, it's very easy to solve this problem. Just take the precondition to be the original matrix. Then it will be identity ideal precondition. But unfortunately, in this case, we will not satisfy the second requirement, that we can easily solve the linear system, because this is the same system we are going to solve. So there is an interplay between the how good a preconditioner is, and it should be as close as possible to the original matrix, and how fast we can solve a linear system with this precondition. So a good idea is that we fix a class of matrices for which we can easily solve linear systems, and then among these matrices find the closest matrix to our original matrix. So that's the general idea. So one of the options to construct preconditioners comes from so-called other iterative methods. Okay, so we are finished with iterative methods, but we are not. There are also some of the iterative methods that you have probably seen before, but okay, no one uses them except for preconditioning Krylov methods. So you've probably seen Jacobi method. Who have seen Jacobi? Who have not seen Jacobi method? Who doesn't know what's doing? Okay, for you it's okay. Gauss-Seidel. Probably you should. Well, if you are from, and also there is a successive over-relaxation, sorry. And symmetric successive over-relaxation. And originally these were just methods that solve a linear system, not preconditioners, but the convergence was not very good. So that's why basically people started to use such methods as preconditioners, and then in some cases it works very well. So it was not directly clear that this can be used as a preconditioner, but now we will show first how to get this method as an iterative method, and second, how to rewrite this as a preconditioner for the original matrix, so you can use it in a general framework of an iterative solver. So the simplest method is Jacobi method. Suppose you have a matrix with non-zero diagonal, and we can rewrite our linear system as a fixed point iteration by taking out separately the diagonal part. So that's the equation for the diagonal element, right? So xi equals to some weighted sum of all of diagonal elements. So in the ideal case, if the matrix is symmetric and positive definite, the diagonal of course, should be positive. Because, well, you need to know the answer why. If you don't know the answer why, you need to find this answer, because this is a very basic question. So if you have a symmetric positive definite matrix, the diagonal is always positive. So that's it's non-zero, so we can divide, and then we can write this as a fixed point iteration. So for example, if you take our favorite matrix, let's try, take it. With -1, 2, -1 here. That gives, well, then you have the equation somewhere in the middle, so we don't have to bother about boundary effects. So we have something like 2xi minus xi minus 1. Have to switch off Telegram probably. So, that's the equation, or maybe something. So, okay, where was I? So we express this, and you get actually a nice iteration. D over 2 plus xa minus 1 plus xa plus 1 over 2. So you basically take the neighboring points, you average them and put inside. So it's sort of interpolation. And this is the Jacobi method. This is the Jacobi method. But we can rewrite it in the matrix form. We can rewrite it in the matrix form. So what's this? So this is the product of the original matrix times vector, but with zeros on the diagonal. If we denote by D the diagonal matrix of the diagonal part of our matrix. So this operator takes the matrix and leaves the matrix of the same size, but with only diagonal elements left. So if you run it in NumPy, the NumPy extracts the diagonal like a vector. So in NumPy you will have to do npi diag over npi diag. It will work. It constructs a diagonal vector output. So okay, here we are doing it on slides. So this is just a diagonal matrix, and this is just, if you take the minus inside, this is just diagonal minus the matrix times x. Okay. And this is the inversion of this. So what we can, how can we can rewrite it is the next iterant is the previous iterant minus the somewhat scaled residual. So this is nothing but Richardson iteration. So with Richardson iteration, we had applied to what matrix? It is applied to the matrix D minus 1A. So what we did,
yeah, it's like kind of interesting because you can have a zero on the diagonal.
Yeah, so we started from the fact that suppose we do not have zeros on the diagonal. Jacobi method, consider again the matrix with non-zero diagonal. Jacobi method works on this. So if you have a symmetric positive definite matrix, the diagonal is always non-zero. So, and in this case, you can also show that the Jacobi method for symmetric positive definite always converges. Actually. So that's the application area. So when you have large diagonal, if you have all zeros on the diagonal, you cannot apply, of course, Jacobi method. So what we are doing here, we're applying Richardson iteration to the linear system D minus 1AX equals D minus 1F. We can also interpret this as preconditioning. So instead of solving an original equation, we solve the linear system with left preconditioner, and this precondition is a diagonal matrix. And this is the simplest example of how you construct a preconditioner. You select the class of easily invertible matrices. So this is the class of diagonal matrices, the simplest possible class. Then you find the closest possible diagonal. What's the closest possible diagonal to your matrix? It's just the diagonal of this matrix. And you invert it. So if you use, so when will it work well? It will work well when the matrix has large diagonal. If the matrix is diagonally dominant, it will work well. When it will not work? It will not work, for example, in the case where all the entries on the diagonal are the same. Then it will be just the identity matrix, that will be a Richardson iteration, and we know everything about the convergence of the Richardson iteration. But if you have, for example, the matrix that has different scales of values on the diagonal, so some is large, some is small, this simple method might work, actually. So